Oh, hello, everyone. The first question goes to Joanna.
Okay, so my question pertains to just the idea of acids usage on page 22 of the chapter 21 enolates. And
You talking
I'm
about the textbook?
no, not the textbook, the
Slides.
slides.
Okay.
And over here, I'm unclear.
Which number again?
Slide 22.
Okay.
So over here, I'm just kind of unclear. So does HCl or any acid kind of cause the removal of an ester?
Okay. Well, esters can be hydrolyzed to carboxylic acids with
Yeah.
either acid or base.
Mm-hmm.
So 3 out of 4, no, half of these show base, the first one, the last one.
Mm-hmm.
And then it's better to make the carboxylic acid and then eliminate them by that six-member ring, three arrows mechanism from the last chapter.
Yeah.
And so that's the most expedient way to do it. But hey, if you just want to do it by adding acid and heating it, that'll do the hydrolysis and decarboxylation as well. So it's a matter of choice, convenience, other things that might be in a more complicated model that we won't see here. So it's just two different ways to accomplish the same thing. So
Um,
for an exam, I would accept either one.
okay.
But for
Just
exam, I might use either one. So you have to be aware of both of them.
just the thing I'm confused about is the example 2 and 3.
Yeah.
Um, one has a carboxylic acid and one is just a ketone.
Well, yeah, that's just the ester here. You can see me.
Oh, yeah,
This
yeah.
ester also will get hydrolyzed and it's going to end up here. The squiggly line is the new bond.
Okay.
So this carbon and this carboxyl group is this carbon, this carboxyl group. It gets hydrolyzed under the same conditions. You can't tell it which ester you do and don't want hydrolyzed if they're too similar.
Okay.
But it won't decarboxylate because that requires a carbonyl group here, and this one's here.
Mm-hmm.
Okay, so sometimes I put on fancier examples just to show you the possibilities, but I also do it here for the second one to show you, hey, that carboxylic acid is stable. Make
Okay.
sure that students look at this relationship. It's a beta keto acid at the end with the butyl group added, and that's what decarboxylates, not alpha, not gamma, just beta.
Is it okay if I ask another question or?
I don't think anybody minds. We usually
Okay.
run out of questions before we run out of time.
I do have a question on the same presentation on slide 31.
Yeah, I'm just going back here just to make sure everybody's on the same map. And where the heck is it? Yeah, the decarboxylation mechanism is here someplace. I'm not seeing. Oh, here it is. So this is the beta keto acid, and they're inherently unstable. They don't decompose rapidly unless you warm it up, but excuse me, but they will do this. You can't stop it, right? It's just set up to do it. And it has this hydrogen bond here. I haven't shown the dotted line, but there's a hydrogen bond here. And it's this 6-electron transition state that's casually referred to as an aromatic transition state, just because it looks like aromatic resonance, not because it's anything essentially aromatic about it. Okay, and you had another question on the same slide set from before?
Yeah, on page 31, um, I was just staring at the ester alkylated with ester.
Mhm.
So over here, you're using the same ester, right? to
Yeah,
alkylate.
it's the same ester. The standard Claisen condensation is a kind of dimerization. You can only call it dimerization if everything's kept, and it's not here. But informally, you can say it's kind of a dimerization. So the enolate drawn here is the nucleophile, but the undeprotonated ester here is the electrophile.
Okay.
So this just undergoes the addition elimination to make the product here, but you have sodium ethoxide present. So this is going to be deprotonated.
Okay. Is it okay if we jump to slide 33 then? I
Yep.
understand this a little bit, but like
This is the
the
tricky one.
yeah, this is something I kind of don't
This
understand
is the
well.
if you understand this slide, you really got it.
Okay.
You might do okay without it, but this is that one step further that shows you you'll do it. So just back up. Okay, so here I mentioned it deprotonates at the end, and that
Yeah.
helps drive the reaction, because the reaction shown here can have problems. So if you use the isopropyl here, all you need is 2 carbons on here, a branching point. Now you're going through a very hindered intermediate, and the product's a little bit hindered, and it's just a non-starter. You can't do this. You might be able to detect the product, but it'll be very low concentration, and it won't change because it's an unfavorable equilibrium. Okay, so you can't make a quaternary carbon here in the middle. Going on to the other slide, the next slide, if you take the product from this slide made a different way, the compound's not impossible to make. It just is unstable in the presence of sodium ethoxide. So make it a different way. We don't have to worry about that too much. If you make it and subject it to sodium ethoxide, well, it's going to attack here, and you're not going to see it because one ethoxide might switch for the other. If it attacks here, now it can cleave the same way as this equilibrium shows. So it can go from here back to here. Okay. And this is going to be the product, and that can't do anything because it can't do a Claisen all by itself. Okay.
Okay.
So
Yeah,
that's the basic stuff. The bottom of the slide takes the thinking a little further. Okay. And I would probably not put this on an exam, but I never make any guarantees about what goes on exams. Well, in terms of topics, yes. In terms of difficulty, no. But this is challenging. Here I switched to methoxide and the methyl ester. I mean, there's nothing magic about it, but you pair them because you can get ester exchange. So anyway, with that said, this is going to attack here and cleave to these 2 compounds. So there's a retroaldehyde, we're done. Well, that's not Orgo. You got to think about what you've made and what else might happen. We don't do a lot of that, but you need that type of thinking to really do well in this course. So let's think about it. Well, this can deprotonate, and it can't do a Claisen because it's going to make this kind of hindered grouping shown up here. This can deprotonate, and now it can react. Okay? So it might be easy for someone to say the bottom right compound is the product. Well, that's absolutely a justified product, but the enolate here can react with this carbonyl group, and you're going to get this product. So you're going to get 2 products out of this. There are 4 possible products, but 2 of them come from the anion of this ester, and it can't do a Claisen. So you get the other 2 products with this as the nucleophile, and either this or this is electrophile. So you're going to get these 2. Okay? I hope that helps.
Yeah, that was good. Thank you.
Okay. Yeah, I mean, that's tricky. somebody asked me to confirm the test is on Friday, not Tuesday. Tuesday, we're gonna finish this chapter because we didn't quite finish, and then we're gonna have practice time. Because this chapter is worth practice time. Next question. Not a great turnout today. I guess the test is too far away to people to be worried yet. But you guys are here, so thank you. Very short session if nobody asks a question. Rua, am I pronouncing that right? I don't remember.
Yeah,
Okay.
yeah.
Seems like
Um,
obvious, but that's names are never obvious.
this is based on the carboxylic acids chapter.
This one,
Yeah, make sure. Slide 58.
58.
Yeah, so for this one, the in-acid mechanism for the last step, can it be the amine that deprotonates or does it have to be water?
Uh, that's a great point. It'd be better to use the amine, but the amine is going to get protonated so quickly, I wouldn't consider this wrong. But if you put the amine there, fine, it's going to get protonated somehow. But being an
Okay,
acid, and being an acid media, I just consider the amine getting immediately protonated, not available. But I give credit for it.
and would you want us to give those byproducts? Like for example, I think it's the slide before this one. We had the protonated amine for the
Okay,
in-acid.
the general answer to either reaction, acid or base, is you draw the neutral acid and neutral amine. Okay, that you get credit for because we draw products in the neutral form in general. But if I said what's present in the reaction flask, now you have to show the carboxylic acid and the protonated amine because that's what's in the flask. Okay, and I haven't asked that question for a long time, but I used to ask it routinely, and someday I'll get in the mood to ask it again. So it's a question of know what are the neutral products you're going to isolate from this reaction, but what is in the flask at the end of the reaction, because you have to know that in the lab to proceed.
Okay, and then when we draw a mechanism, do you want us to include equilibrium arrows where it's appropriate, or can we just use regular arrows?
If I don't ask, just use the regular arrow.
Okay.
The mistake students make is sometimes they will use the resonance arrow in a mechanism, and that's wrong. I hate taking a point off for that, but it's wrong. Yeah, they don't understand the arrows and their meaning if they make that mistake. Either that or they really need to learn to proofread. Uh, Christina, give me a second. That's a good question. I don't want to forget about it. Um, oh, yeah, I'm sorry, I'm not thinking. Okay, it was set to automatically release, but I assume you were requesting it sooner, not later. It's available now. Chapter 21, I didn't look at that one. It should be out. Yeah, the carboxylic acids was already there. The enolate is now there. So if you have time to go through it, you can bring questions on Tuesday.
Professor, for the same presentation, slide 55, is this mechanism similar to the one on slide 54 with the carboxylic acid?
55. "55" is the high temperature production of amide from the acid and carbon and amine. They're not related, 54 and 55?
Yeah, I just thought that like if I were to draw out the mechanism, I I mean, I don't know if we have to know it, but would it be the same steps? Because I mean, it's amide formation, so I just thought it'd be similar.
No, not really. This is much easier. The
Mm.
nitrogen here is nucleophilic. It's gonna attack here. Your weak base is gonna deprotonate it. Yeah, it would have some similarity. It would. Yeah, at this point in Orgo, I don't see putting down different mechanisms that are really similar. So if you know this well and apply it to this with the same thinking, you'll do fine. If you only know the mechanisms you specifically remembered, your understanding is little bit less than it should be. But my bias is to ask about the ones I showed. But I have modified that a little bit. Sometimes I put in a surprise. Let's see how they do with this. And this evil laugh in the background.
And actually for carboxylic acids, the Fischer esterification and the acid hydrolysis, I think I'm getting a little confused because there in some steps it says to add acid, but I would imagine to use just like the regular alcohol, not the protonated alcohol. For example, step 3 and step 6. Can't we just
I'm not specifically stating the acid here, just to keep fewer letters on there. I've wanted to change these all to put quotes, right? Because I don't give credit for that, but this isn't a full mechanism. This is a suggestive mechanism without all the arrows and everything. So this H plus will be delivered from protonated ethanol. Okay, and then ethanol attacks, and then ethanol deprotonates. So when ethanol is your solvent in this reaction, it's the proton carrier in the base. Okay, so you guys have seen that. Here, yeah, it's just backwards because every step's in equilibrium. And this is a good example of how base catalyzed reactions are always fewer steps than acid catalyzed reactions. I don't know if that's universally true, but it sure is close if it's not.
why is it that the OR group can leave even though it's like it's going to be an anion when it leaves? Why can we do that?
Where are you? Oh, here?
Yeah, the base hydrolysis.
Okay, we discussed this, somebody in my office last week. You're taught in Orgo 1 that alkoxides, hydroxides are lousy leaving group, and they're never leaving groups, and the book leaves it there, and they do you a great disservice. They are not leaving groups in SN1, SN2, E1, or E2. This is not any of those. This is kind of like that ECB we covered on Friday. There's an anion here, and it's going to make a new bond and kick out an anion of comparable stability. That's fine. That's not E1, E2, SN1, or SN2. Okay, so one O minus can make the carbonyl and kick out another O minus. Not a problem. That's the way it works. And this reaction under standard conditions is usually done in half an hour to an hour. It's at room temperature. I've done many of them. They're the kind of thing you set up, you go to lunch, you come back, you check it to make sure, and it's done. Not that I ever went to lunch when I was doing research. Even in industry, I joke that if I ate lunch sitting down, my stomach wouldn't know what to do with it. You know. Mehr Fragen? Más pregunta? I've forgotten every French word I ever learned, so I probably never could have said that in French. I only took 1 year. 1 year of any foreign language, yeah, not much.
Actually, Professor, can you go to slide 94? I just wanted to see if you could write down the mechanism that it's asking for there, just to make sure.
94. I have a file open. And it's no longer ChemDraw. Oh, well. What's the mechanism we're looking for? Esterification or no, amide formation?
It's with pyridine, the anhydride, and methanol.
Oh, methanol. So I hate the defaults on ChemDraw. I don't want you to cover my entire screen when you come up. The first good incarnation of ChemDraw was fine, and it never got improved after that. Okay, so that's what I'm asking for. The anhydride methanol pyridine. I am just going to draw down the compounds with no arrows. And then if somebody wants arrows added, I can add them, but that takes quite a bit of time. Need this now. Is that big enough?
Yeah, I think that's good.
Ooh. So again, you'll have to imagine the arrows, but I can add them at request. It's going to attack carbonyl. They're the same, so it doesn't matter. Okay, now everybody tell me what I'm missing. Little practice. Something's grossly wrong with this. We got a nitrogen.
Be a positive charge on the nitrogen.
Yeah, nitrogen has 4 bonds. And there's no hesitation. If you don't put a positive charge there, your back should crawl. Okay. So yeah. Okay, so now we have acetate. And now I would not be picky on this. You could deprotonate with the methanol and then attack. Or just attack with the methanol. I see either one of them as not being unreasonable. Um, if you choose methoxide by deprotonating it with pyridine, I'm really not sure which would win. But pyridine's a pretty bad base for an alcohol, so. Let's see, okay, I'll be right back. Somebody has come home. Hello, I'm in my session. I'm in my session, my students. I'll bring stuff in later. Okay. Yeah, so you have to do a deprotonation step here to make methoxide or here to make the final product. And I would give credit for either one. You could argue advantages one way or the other, but. So who asked me to do this?
Yeah, that was me. This makes sense. Thank you.
Yeah, it's fine. More questions? Only got a dozen of you today. So you guys are gonna have to step up with questions if you want questions asked. Gonna have questions from the homework that I post.
Okay, I guess for slide 60, what do you mean by go on to the acid?
Either one of these can be hydrolyzed or the same compound. They can be hydrolyzed to carboxylic acid. We already show that. So this is hydrolysis of nitriles. And you can stop at the amide because this first step, part of the hydrolysis, it's a double hydrolysis, right? Actually, it's a hydration followed by hydrolysis, just to be technical. The hydrolysis itself isn't shown because it's shown here. Okay, so this is just adding the part you need to go from the nitrile to the amide and then back up a couple slides for the rest.
Oh, okay, so if this was an exam question, we would have to show it going completely to the carboxylic acid?
Well, you have to read the instructions and do what's requested. Okay, so I would be specific as to whether I wanted the amide for the product or all the way to the carboxylic acid.
Okay, thank you.
And you've got to admit, these two aren't that hard, right? Just to the amide.
Yeah.
Although, what's the acidity of a nitrile nitrogen, the lone pair on the nitrogen? I'm sorry, the basicity? Pretty bad, because it's an sp cubed, or I mean an sp nitrogen, but they can be protonated. You just need a trace. I actually don't know a pKa number. I just know it's, not acetic acid. I don't think we'll do this. Any more questions? I mean, you can bring questions to lecture on Tuesday. We'll have time for them.
I actually have are we allowed to ask questions about like the recitations?
Oh, absolutely. Anything that teaches Orgo.
Okay, so from the most recent recitation, there was a question asking to rank like compounds in order of increasing pKa, like the acidity, and I don't fully understand.
That was from the homework, the question itself.
I'm not sure if it was, I just got it from Sharon.
Probably where it came from. I'm sorry, who's your recitation leader?
Sharon?
Okay. Oh, I already have the homework open. Where is it? This question?
Yeah, but it also had additional compounds. There was a few more.
Yeah, well, she might be doing her own questions. I told them from the very beginning that they can do what they think's in their students' best interest. Not every recitation section is equally strong or have the same personalities. So we can do this if you want and then add to it.
Yeah, that would be great. Thank you.
Okay, do you have a good feeling for the numbers here and why they are what they are?
Not really, honestly.
Okay, well, alcohols, you kind of know, right? They're a little like water, but less acidic. So secondary alcohol 17, yeah, it sounds right. And generally on an exam, I almost always ask you to, no, I don't think I've ever not. I ask you to rank them. And then if you want more generous partial credit, you can put down pKa's. So I don't have to, I do guessing corrections when it's like that. So anyway, ketones are only a little less acidic. They're a little slower to deprotonate, but I wouldn't ask about that. Carbon, taking up proton off a carbon is got a little bit higher activation energy, even though acidity. Acidity is a thermodynamic number, not a kinetic number. Okay, and we're asking here for the thermodynamic numbers. So anyway, ketones are a little less acidic. Esters are a lot less acidic because this carbonyl is in resonance with this oxygen to some extent, and that lowers this. Okay? And now you've got the triple ones. So if a ketone's more acidic than an ester, then the diketone is going to be the most acidic. The ketoester is going to be next, and the diester is going to be the least. Well, because they're doubly stabilized, they're now more acidic than the alcohol. We learned in lecture that you can completely deprotonate 9, 11, or 13 with ethoxide. Or sodium hydride works too. You can't practically deprotonate a ketone with sodium hydride. Not that I've ever seen. It would be very slow. There'd have to be some trick going on. But these dye-safe substitute enolates, yeah, sodium hydride's all you need.
Okay, thank you.
Yeah. Was there any other species that you'd like me to include comments on? If I asked for a phenol, yeah, it'd be in this game. 9, 10, and 11, yeah, I'd go real easy on grading that one. But if I gave you paranitrophenol, now would be the most acidic one here.
And an amide would be the most basic here, right?
Amides are even harder to deprotonate. Yeah, the enolate would be the most basic because amides have a lot more of resonance.
Okay, thank you.
So you have to give up the resonance to stabilize the anion. And, I expect you to learn the acids that I teach you, but with enough understanding that I can throw a question in there with comparisons you haven't seen before. The harder it is, the easier I go on the grading, but I expect you to make your best guess. If you see a question on exam, I don't know this. Yeah, that's probably the hardest question on the exam. Just do your best.
Professor, can you actually explain one more time why the diketone and the diester and the ketoester are more acidic than the alcohol?
Well, just think of what an ester is, an enolate of an ester. You got a double bond between the two carbons and an oxygen negative charge. It's not that different. In fact, because the double bond, when you have the oxygen with a negative charge, you have sp4 carbons, you might guess that an enolate is more stable than alkoxide. But there's subtle things that go on. So you just have to remember that an ester or a ketone enolate is basically a fancy alkoxide, and so it must be somewhat similar. And then, if you then have one of these other species, you got two oxygens helping carry the negative charge in resonance. And so they must be more acidic.
Oh, I see. Okay. Thank you.
That's a big change now.
Yeah.
is a good question to practice resonance structures. And is anybody awake enough to know which resonance structure is missing? Two of them, actually. Resonance is a universal topic in Orgo. There is no exam where I don't know if there's an exam in Orgo 2 where resonance isn't a question or necessary in your thinking to answer a question. So I have written this acetyl group here with the oxygen here and the carbon here. You can rotate that and put it the other way around, in which case the oxygen anion is here and the methyl group's here, and that's a different resonance structure. But you can't have them both existing at the same time. You know, if once you have this resonance, you can't switch these two because it's got double bond character. But starting here, yeah, there's actually 4 ways to go, depending on which way you orient these. I think the complexity of it indicates that I only want one set, not all 4 sets. It'd be getting kind of silly, and you wouldn't like the time and paper it would take. Oh, here, I'm following up that. For 2, you can guess that's not what I want. For 3, all the enols of this, yeah, this enol and this enol are different because of the double bond character. So number 3, it's pretty tricky to find all 5 of these without really clear thinking. Yeah, that's my homework. If you haven't done it before, yeah, it's my homework. Five is a nice mechanism to hone your skills. Eight is just drilling reactions. So if you haven't done this, yeah, this is just drilling, practice, practice, practice. So these aren't hard, these aren't inherently hard questions. They're, yeah, I need more practice questions. Yeah, this is a great homework if you have time before Friday's exam. But you can skip some of these. Yeah. Yeah, if you're good at resonance, skip that. This one definitely skip, you know, if you don't have, if it doesn't speak to you right away. Seven is probably not going to be on an exam ever, but it's good practice. And the rest of this is just regular practice, nothing challenging about it. I write kind of long homeworks, don't I? It's what's needed to learn Orgo. So are we done, or are there more questions?
I just have a question on using reagents that we learned from the textbook as well. Like, would you prefer reagents from your slides more than the textbook?
I prefer you to put down whatever answer that I can give you full credit for, whatever makes you more comfortable. If it's a reagent from the textbook or even a different source and it works, I'll give you credit. Only once has somebody put down a reagent I wasn't familiar with. I don't know where they got it. I think they got it at CHEG. Sometimes CHEG will have somebody showing off all the minutia of detail they have. I think it's where they got it. And I looked it up. I gave them credit. You know, they pointed it out to me and I checked it out and said, yeah, you get credit. But, you know, you might want to stay with things close to what we learn. But, you know, correct is correct.
Okay, thank you.
Now, if you find something on the internet that contradicts what I teach you, yeah, I can't give you credit for that. There's bad Orgo out there. Okay, I'm assuming that's all for today. Unless somebody is just waiting with a question, hoping somebody else is going to ask it.